Can't believe I forgot that part. Can you? How are we doing here? I was handing back tests, yes. All right. So, an n-by-n matrix is diagonalizable if and only if we have a complete set of eigenvectors. That means we have to have n linearly independent eigenvectors or we don't have a basis. If we have a fewer number because it's defective, then we don't have enough of them to diagonalize. The diagonalizing matrix is called X, the matrix whose columns are your chosen eigenvectors, but if you choose different eigenvectors or choose them in a different order, you get a different matrix X. But the one you get, you're going to call A diagonalizing matrix X. But we can also multiply, come on now, move. If we have D equal X inverse AX, we can multiply both sides by X on the left and X inverse on the right. And this is called the diagonal factorization, a diagonal factorization of A. And why? What this does, X translates vectors from the eigenbasis into the standard basis. A performs the linear transformation in standard bases. And then X translates that vector in standard basis vectors back into wait. I wrote something wrong. D is X inverse AX. Did I do that right? Yeah. Okay, I'm just saying it badly. X inverse translates the vector from standard coordinates into the eigenbases. D represents the linear transformation, but now all you have to do is stretch and squish the eigenvectors, or multiples of the eigenvectors. And then X translates that answer in eigenvector basis back into the standard basis, right? That's why it factors A into a non-singular matrix X and a diagonal matrix D. Okay. What's interesting about that is, how do I figure out A squared? Well, if A squared is XD X inverse. A typo? No. Then A squared is, if A is XD X inverse, then A squared is XD X inverse times itself. And multiplication, while not commutative, is associative. So I can reorder it X times D times X inverse times X times D times X inverse. Which means that the X inverse X's in the middle become the identity. And the identity times D is D. So if I need A to the 50th power, I can just calculate D to the 50th power and then multiply it on the left by X and the right by X inverse. And it's a lot less work. Why is it such a lot less work? Because how do you square a diagonal matrix? Right? To multiply these two matrices, it's lambda 1 times the first column, plus 0 times the second column, 0 times the third column, 0 times the fourth column, 0 times all the columns. Right? So in the first column of the answer, you get lambda 1 squared. In the second column, you get 0 times the first column, plus lambda 2 times the second column, which is lambda 2 squared, right? And then all zeros, which means that's when you square a diagonal matrix, you just square the elements of the diagonal. When you cube a diagonal matrix, you just cube the elements of the diagonal. If I want the 50th power of a diagonal matrix, I just raise each of those numbers to the 50th power. Much easier than multiplying matrices times themselves. Right? It takes, on the order of, for an n by n matrix, n cubed operations to square a matrix. But to square a diagonal matrix only takes n, because you just multiply each of the elements of the diagonal times itself. N cubed is a much bigger number than n. Yeah?
So out of curiosity, are a lot of the matrices used by like computers and systems, are they a lot of them diagonal? Or?
No, but the thing is, okay, If you're doing statistics, if you're doing a population study or data mining or data science, if you are trying to extract information, or you are doing control theory, or you are trying to detect imperfections in a concrete wall or in a carbon fiber structure of a plane, all of these involve physics problems that have diagonalizable matrices. So if your detector has to make 8K measurements per second, then we diagonalize that matrix first to make the multiplications as quick as possible, right? And then as they come in, all you have to do is keep multiplying the diagonals times each other, and then, right? So what happens is in hardware, in firmware, you perform some other type of operation that represents the information in a basis of your choosing. One in which all the operations you need to perform are algebraically simple, right? That can be performed by a regular CPU or a GPU quickly. That way, the detector runs as quickly as possible, so you can get as many observations per second as you need. It works the same way for creating a television set. If you have 4K by 4K pixels, you have to be able to render, even though you're only doing a fourth of the screen each, you have to be able to render 1 million pixels really fast. And that involves simplifying the arithmetic as much as possible. And this is where diagonalization is used, or whether some of the other bases we're going to talk about are used. But we're going to focus mostly on diagonalization. Okay, let's take a look at this matrix that has columns 0, -3, and 4, 8. And we want to ask ourselves, what is the diagonalizing matrix for this matrix A? That means we need to find the eigenvalues so that we can find the eigenspaces, so we can choose eigenvectors to be our basis vectors, right? So first, we create the characteristic polynomial by computing the determinant of A minus lambda I. We get minus lambda times 8 minus lambda minus -3 times 4, which is plus 12. Okay, so in the take-home test, someone completely ignored the rubrics, and they needed to calculate the determinant of a 3 by 3, and they just went straight to 3 2x2s. They didn't use any of the properties of determinants. They just wrote it as 3 2x2s. So I took points off, like I said I would. Okay. Well, this gives us minus 8 lambda plus lambda squared plus 12, and lambda squared minus 8 lambda plus 12 factors into lambda minus 6 times lambda minus 2. Here's the deal. After you leave college, they never factor like that. They're never 2 and 6. So you're going to use a computer a lot to tell you what the two roots are. After all, you're going to resort to the quadratic formula, yes? Okay. For example, in the textbook, the author does them, might do 2 first and then 6, or 12 first and then 4. The thing is, the next thing we have to do on Wednesday, the order is important. So we might as well start doing that now. Always start from the largest positive eigenvalue to the largest negative eigenvalue, right? Or for you guys, this way. So 6 is the largest positive eigenvalue, and then go right to left. And the next largest one is 2. So if we subtract 6 for lambda, we have minus lambda and minus 3, and 4 and 8 minus lambda, 2, 8 minus 6, 2. And we ask ourselves, what's the null space? So we reduce it. And we get that, the span of 2/3 and 1. Since there are infinitely many eigenvectors, and we can choose one that doesn't have fractions, right? I'm going to choose another vector on that line, 2, 3. Well, how did I get 2, 3? Well, I had a 2/3. So I used alpha equal 3 in my span, right? It's any multiple t times 2/3 1, so I let t equal 3. I just like 2, 3 better because they're integers. I don't have to deal with fractions. Do you see why I did that? Okay, now, when we look at the other eigenvalue 2, we're going to get -2, -3, and 6, 8 minus 2, 4, 8 minus 2, which is 6. We reduce it, and we get the null space is the span of 2, 1. Okay, so our new eigenbases are the basis vectors 2, 3, and 2, 1. This forms a basis for R2, and its transition matrix from the eigenbasis to the standard basis would be given by X equal the matrix with columns 2, 3, and 2, 1. So not much work to do there. And we know our diagonal matrix D, because we chose the biggest eigenvalue first, and now I want you to get used to this. Always put your biggest eigenvalue up here in the top left, the biggest positive eigenvalue up in the left-hand corner, and go along the number line from right to left. Okay? So that they get smaller and smaller. Okay. And that means that x inverse AX is going to be the inverse of x times A times x. And the inverse of A, since it's a 2 by 2, we'll use one of the term times the transpose of the cofactor matrix, the adjugate. And that comes up, and we get 6002, so we knew we didn't make a mistake. Does this make sense? This is called solving the eigenvector value problem, or solving the eigenvalue problem. Now, there's another video for you to watch before Wednesday. It is a beginning of understanding why the exponential function became so important. Why do we make high school students study it? Why do we study it in Calc 1 and Calc 2, and we keep studying it? Has anybody taken linear algebra already, or is currently enrolled in it?
Who's linear algebra?
Huh? Diffie-Q, differential equations. E to the kx turned out to be super important, didn't it? All right, so this is about not just exponential matrices, but differential equations. And it talks about why our mathematical models, the exponential function and the natural logarithm, keep popping up everywhere. But can we calculate E to a matrix? Well, it depends. What if the matrix is a diagonal matrix? Does everybody recognize that definition of e to the x? That's its Maclaurin series, right? It's x to the 0. Anything to the 0 should be the identity matrix, right? Over 0 factorial, and 0 factorial is 1, plus d to the 1 power over 1 factorial, plus d squared over 2 factorial, d cubed over 3 factorial. Wait a minute, don't I know how to square and cube and raise diagonal matrices to positive powers? Integer powers anyway. Yeah. So, I can write it using our fancy Greek capital S, sigma. This is the Maclaurin series. And now I've replaced d to the k with what it kind of looks like. Right? But when I add up, when I'm multiplying by k factorial, can't I just go ahead and multiply this matrix by k factorial and get k factorial in here? And when I add a bunch of matrices, isn't it the same thing as just, there are zeros everywhere else. Can't I put the sums inside the matrix? Because when we add matrices, we add corresponding elements, and there's nothing else involved in the first element, element 1, 1, except element 1, 1, and nothing with element 2, 2, except 2, 2, and KK except, or JJ except JJ, and NN except NN. Well, wait a minute. Don't you recognize these n limits? This is e to the lambda 1, n, right? And this is e to the lambda 2, and this is e to the lambda 1. So if D is a diagonal matrix, E to the diagonal matrix is the matrix that has E to the lambda k all along the diagonal for each of the diagonal elements. Well, how do we calculate E to the A? If A is diagonalizable, then we can do it. How do we do that? We replace A with x dx inverse. Now, this means this k goes in here, and these remain x's and x inverses. But can't we distribute the x and the x inverse? And this is e to the d. So if A is diagonalizable, e to the a is x e to the d x inverse. And in the 19th century, in David Hilbert's time, this was considered really, really abstract mathematics. But it didn't take long until just after that, Einstein wrote his paper on special relativity, and now e to the a turned into became super important. The key to keep in mind, there were other mathematicians and physicists coming up, Dirac and others, all working on similar types of problems and realizing that if they want to linearize the problem, they're going to end up with e to the kx or e to the dx. Now we won't use d. Dirac always used t for time, right? So you get e to the at, where a is a matrix. So you have e to the at would be x e to the dt x inverse, which would have lambda t along e to the lambda t along the diagonals. For example, let's compute e to the ax from our example above. We found out our two eigenvalues, and we know what our diagonalizing matrix X is. It's the one with eigenvectors 2, 3, and 2, 1. We know what X inverse looks like. And e to the d is the diagonal matrix with e to the 6 and e squared along the diagonal. Now we multiply, and then multiply again. And what does this look like? What is the actual, honest-to-goodness definition for mathematicians for sine x and cosine x? What? Right. Euler proved that e to the ix is cosine x plus I sine x. And we can calculate this even if X is a diagonalizing matrix, diagonalizable matrix A. And that makes e to the minus ix cosine negative x, which is cosine x, plus I sine negative x, which is minus sine x. So, what happens if we add these two equations together? I get 2 cosine x equals the sum of the left-hand side. So cosine x is e to the ix plus e to the minus ix, all divided by 2. What if I subtract the second equation from the first equation? I'll get 2I times sine equal the difference. So sine x is e to the ix minus e to the minus x divided by 2I. And unfortunately, complex numbers come up. But you also know another identity, e to the x plus e to the minus x over 2 and e to the x minus e to the minus ix, minus x over 2. What are these called? This is the hyperbolic cosine. You see how similar they are in definition? And the hyperbolic sine, which come up in physics problems. Why? Because there's got e to the kx and e to the minus kx in them. So in your differential equations, if you come up with a characteristic polynomial, which is the same thing it is in this class, and you get complex conjugate roots, it tells you you have cosines and sines. You have periodic motion. And you can write it using complex numbers, as double E's will often do now, in this, since about 1950. Or you can make a change of variables and rewrite it in terms of sines and cosines, which is what a lot of other people do. Okay. Okay. Which means that some of our eigenvalues are going to be complex, and some of our eigenvectors are going to have complex numbers in the vector. So we need to know a little bit about that. Not a lot, but we need to know a little bit about it. And there's a lot of vocabulary going on here. And it is not in the textbook. It is in the appendix to the textbook in the electronic version. I don't know why they did that. Okay. Even if something is a complex number, complex numbers have a geometry to them as well. Only now the vertical axis is the imaginary axis, and the horizontal axis is the real axis. And A plus BI gives us a right triangle with base I, A, and height B. And so the magnitude of the complex number is going to be the square root of A squared plus B squared. Well, how do we get A squared plus B squared out of A plus B times I? Well, A plus B times I times its complex conjugate, A minus B times I. So Z times Z conjugate. Oh no, we can't have bar over the top mean vector and bar over the top mean conjugate. Okay, there are several ways to handle this. Some people use a hat, but we use hat already for something else. Some people physicists like to use a dagger. And I can't draw a dagger very well, but if you've seen it, it's a little bitty fancy dagger. It's called the Hermitian. But I can't draw daggers very well, so I write Hermitian. What is the Hermitian? It's the complex conjugate transpose. But the transpose of a 1 by 1 is just the 1 by 1. All right? So it just means complex conjugate. And you get this is A plus C times A minus C. That's A squared plus minus C squared. So A squared minus C squared. Oh wait, B squared is the negative 1. So this is A squared plus B squared. So a complex number times its conjugate is equal to its length squared. That looks a lot like dot product. There's a problem. If we have two complex vectors, how about a vector in C2? What about a vector in C2? Right? The set of all 2 by 1 complex valued vectors. Let's look at an example. 2 minus I, 1 plus 3I. Now let's multiply it times its Hermitian. Let's see here. No, we don't want to do that. The Hermitian of a vector is its complex conjugate transpose. So it conjugates every element of the vector or the matrix, and it transposes it, both. It has to do both. Well, we're going to get 2 minus I, wait, come on now. 2 plus I times 2 minus I, because we're going to multiply corresponding elements, plus 1 minus 3I times 1 plus 3I. That gives us 4 plus 1 plus 1 plus 9, which is 15. So the dot product of two complex valued vectors, u and v, is the Hermitian of v times u. In other words, it's complex conjugate transpose. And so that means complex dot product is not commutative.
because V dot U is U Hermitian times V. And what is that? Well, we're going to learn in a second. If we want to get Hermitian outside the parentheses, because it's a transpose, we have to switch the order of operation. So we have to review some stuff that we learned a long time ago about complex numbers. One of them is the complex conjugate of the complex conjugate is just the original number, right? The complex conjugate of a plus bi is a minus bi, and the conjugate of that is the a minus a minus bi, which is a plus bi. The complex conjugate of w times z is the complex conjugate of w times the complex conjugate of z. And if we have a real number that's a plus 0i, then the complex conjugate of a real number is a minus 0i. It's just a. The complex conjugate of the sum of two complex numbers is the sum of the complex conjugates. And because it works for multiplication, and the complex numbers, unlike R2, is a field, the conjugate of the quotient of two complex numbers is the quotient of their complex conjugates. Is this all coming back? Now, in matrices, we learned in chapter 2 that A times B transpose is B transpose times A transpose. And we know that A Hermitian is A. We know that A plus B is. And why do we know this? Well, we know that for every complex value in the matrix, the sum of the sum of the conjugates is the conjugate of the sum, and we know for transposes, the transpose of a sum of two matrices is the sum of the transposes. So, how would we show this is true? We would say that A plus B Hermitian is the complex conjugate of A plus B transpose, which is the complex conjugate of A transpose plus B transpose, we learned in chapter 2. And the conjugate of a sum is the sum of the conjugates, which is the conjugate of A transpose plus the conjugate of B transpose. And that's the Hermitian of A plus the Hermitian of B, because it's the complex conjugate transpose of A plus the complex conjugate of B. And this gives you an idea about all of it. That means, of course, that the complex conjugate transpose of A times B is going to be the conjugate of A times B transpose, which is the conjugate of B transpose times A transpose, which is the conjugate of B transpose times the conjugate of A transpose, which is the Hermitian of B, the complex conjugate transpose of B times the complex conjugate transpose of A. Not too bad. Okay. Do you remember on the first test I asked you a question about real symmetric matrices? I said if a matrix was symmetric, that means A transpose equals A. So what are we going to call it if the Hermitian of A equals, if the complex conjugate transpose of A equals A? We're going to call it a Hermitian matrix. Well, if we have the complex conjugate if we have the dot product of two complex valued vectors, it's the Hermitian z times w, then the dot product of any vector with itself will be its Hermitian times itself, which will be the conjugate of w1 times the conjugate of w2 times w1, w2, which will be the conjugate of w1 times itself plus the conjugate of w2 times itself. But remember, w1 and w2 are complex numbers, not real numbers. The complex of w, now how are we going to do that? Let's call w1, let's call w1 a plus bi, and w2 c plus di. Then w1 Hermitian times w1 is a minus bi times a plus bi, which is a squared plus b squared, because I squared is equal to a negative 1. Come on. And w2 Hermitian times w2 is c minus di times c plus di, which is c squared plus d squared. And so, the Hermitian of vector w times itself, in other words, its dot product of w with itself in complex dot products, is the Hermitian of w1 plus times w1, a squared plus b squared, plus the Hermitian of w2 times itself, c squared plus d squared. And so we can say that the norm of a complex valued vector is the square root of the sums of the squares of all of the elements. And like before, it is the square root of the dot product of w with itself, the square root of the Hermitian of w times itself. Okay? Why did we go to all this trouble? Well, we'll go into it a little more next time, and hopefully it'll make a lot more sense, because this is the first time you've seen anything like this. But is there such a thing as an irreducible cubic? What? Yeah. Is there such a thing as an irreducible cubic? Or is the only formula that produces complex conjugate roots the quadratic formula?
There is a cubic form.
There's a formula for cubics, but don't cubics always have one real root? Now, we should have learned a long time ago that complex roots of real valued polynomials always come in complex conjugate pairs. Here's a cubic with one real root and two complex conjugate roots. How do I know that? Root is the x-intercept of the graph. And where does the graph intersect the x-axis? At exactly one point, right? So that minimum corresponds to a pair of complex conjugate roots. How many real roots does this cubic have? 3. It touches the x-axis. When it touches, what does that tell you? It has a root of multiplicity 2. Right. Remember, whenever it touches, it has even multiplicity, and whenever it crosses, it has odd multiplicity. It's a cubic. So you know there are only 3 roots, and you know that the one where it crosses and that's negative is one of them. The other 2 are the even root, the root of even multiplicity you get when you touch instead of cross the x-axis. And finally, This one has 3 distinct roots, right? Is that always going to happen? Did you learn somewhere complex conjugate roots only come in pairs? That means they only come as a pair of roots to the quadratic formula. And that all the other roots are either going to be in other pairs. If I have a polynomial of degree 5, I can have 5 distinct roots, 5 roots, all real, or I can have 3 real roots and a pair of complex conjugate roots, or I can have 1 real root and 2 pairs of complex conjugate roots. But that's all that can happen, right? Either get 1 real root, 3 real roots, or 5 real roots. If I have a parabola, if the parabola never intersects the x-axis, then it has a pair of complex conjugate roots. If it comes down and touches the x-axis, it has a real root of multiplicity 2. And if it crosses the x-axis twice, then it has 2 distinct real roots. And they correspond to the discriminant. When the discriminant is positive, you get 2 distinct real roots. When the discriminant is 0, you get a pair of repeated roots, right? A root of multiplicity 2. Minus b plus 0 over 2a, and minus b minus 0 over 2a. And if the discriminant is negative, then you get a pair of complex conjugate roots. Okay, so when we are looking for the eigenvalues of a real matrix, we're either going to get all real roots, or we're going to get groups of pairs of complex conjugate roots. Okay. There are the properties of a complex inner product. Notice we don't use the dot anymore. We use the angle brackets. If the columns of a complex value matrix are all orthonormal, that means that their complex dot products are all 0 because they're orthogonal, and they all have unit length, their inner products with themselves is 1 squared, then we call that not an orthogonal matrix, right, but a unitary matrix. So, if the columns of matrix U are orthonormal, complex orthonormal, then we say U is a unitary matrix. But aren't our orthogonal matrices already unitary matrices? Because the conjugate of a real number is itself. So all real symmetric matrices are Hermitian, but not all Hermitian matrices are symmetric. Real and symmetric, because they could be complex value. All orthogonal matrices are Hermitian. They're real and orthogonal. That makes them Hermitian, but not all Hermitian matrices are orthogonal, because they may not be real, right? Okay. And here are the properties of Hermitian matrices. The complex conjugate transpose of the complex conjugate transpose is the original matrix, because the conjugate of the real numbers inside, and the transpose of the transpose is the original matrix. So the complex conjugate transpose of the complex conjugate transpose does nothing. The conjugates undo each other, and the transposes undo each other. But notice that when you try to move the Hermitian inside the parentheses for a product in property 3, like transpose and like inverse, it reverses the order of the multiplication. And if Z is equal to its own Hermitian, its own complex conjugate transpose, then we say that it is a Hermitian matrix. Look at Z and W. They are Hermitian. If we transpose either of these matrices and then conjugate all 9 of the elements of W or all 4 of the elements of Z, we will get the original matrix back. And you can see that on the page. When we transpose, and we're using bar over the top because the person who made the graphic likes bar over the top, but
when we decided to take Z and transpose it, notice that this column becomes a row, and the second column becomes the second row, but we need the complex conjugate of all four of those entries. Conjugate of negative 1 plus 0i is negative 1 minus 0i, which is negative 1. The conjugate of 2 minus 2i is 2 minus 2i, and the conjugate of 2 minus 2i is 2 plus 2i, and the conjugate of 3 plus 0i is 3 minus 0i. And that's Z. So it's a Hermitian matrix because it's equal to its own complex conjugate transpose. And W, by the same token, is also Hermitian because if I compute the complex conjugate of all of the entries and transpose the matrix, I get the same matrix I had in the first place. Why is this important? Because in a Hermitian matrix, right, in an orthogonal matrix, eigenvectors of distinct eigenvalues are not just linearly independent. They're orthogonal to each other. This is super important. It turns out that if you have a symmetric matrix, a real symmetric matrix, or you have a Hermitian matrix, its eigenvectors for different eigenvalues aren't just linearly independent, they're orthogonal to each other. They're mutually perpendicular. And actually the proof is pretty easy. It uses the property of complex conjugate transpose. Remember, if the complex conjugate of a number is itself, it's a real number. All we had to do was bring this Hermitian inside. And any number that is a real number alpha divided by the length of something squared, which is a real number that's greater than 0, is going to be a real number. A real number divided by a real number is a real number. So we do the same trick we did before. We apply A and get lambda 1 x1, and we apply A and get lambda 2 x2. And when we do that, remember this is the length squared. This is the dot product of these two. And the lambdas are different. So when we subtract one side from the other, we get lambda 1 minus lambda 2 times the dot product of x1 and x2. And the lambda 1 and lambda 2 is not 0 because they're different. And so the dot product of x1 and x2 has to be complex inner product of x1 and x2 has to be the thing that's equal to 0. And when the dot product of two vectors is 0, they're orthogonal. Okay. So what we are going to do at the beginning of class next time, we are going to find the eigenvalues and eigenvectors of a symmetric or Hermitian matrix. We will get eigenvectors that are already perpendicular to each other and divide each one by its length so they're all unit vectors. Wait a minute. That would make all of the columns of our diagonalizing matrix X made up of vectors that are orthonormal from each other, making it an orthogonal matrix, a rotation. So all that will happen is, if we have a symmetric matrix, we rotate it till we line up the axes with the axes that David Hilbert would call proper axes, and then the matrix that represents the linear transformation will be a diagonal matrix. Okay. All right. I'll see everybody on Wednesday.
Do you have a test on Wednesday or next?
No, it's next Wednesday.
Next Wednesday, okay.
This is the last week of class. This is the second to last week of class. Right?
So do we have another test before the final?
Yeah.
Okay.
Next Wednesday, the last day of class.
Okay. Sorry, I was confused and thought it was this Wednesday, then a week, and then.
And if you have some ideas about your project, now is the time. This now is the time for us to discuss it. You may not start working on it right away, but we need to figure out what it's going to be this week.
I was thinking quality metrics for